everyone, and welcome to This Explainer. Today, we're taking a truly fascinating journey into the world of mixtures, and more importantly, how we actually separate them. We aren't just going to sit here and memorize facts today. Oh no, we're going to uncover the hidden behavior of everyday matter. And by the end of this, you'll be applying these very concepts to real-world scenarios. Let's dive right in. Real quick, here is our roadmap for today. First, we'll be classifying types of mixtures. Second, we'll look at particle size and light. Third, we're diving into the science of separation. Fourth, we'll explore our incredible Indian knowledge systems heritage. And finally, we'll see how you can master all these concepts at EduNudge.
All right, Section 1, classifying types of mixtures, understanding homogeneous and heterogeneous matter. Let's go.
So, the absolutely crucial first step here is drawing a clear line between two main categories of matter. On one side, we've got homogeneous mixtures. These have a completely uniform composition throughout. Think of a perfectly stirred glass of sugar water. Every single sip is just as sweet as the last, right? But on the other side, we have heterogeneous mixtures. If you dump some sand into water, it doesn't blend perfectly at all. The sand just kind of settles, leaving these distinct, non-uniform phases. And that brings us to some everyday examples you've definitely seen. True solutions, like salt dissolved in water, are perfectly homogeneous. Suspensions, like chalk powder shaken up in water, are clearly heterogeneous because, well, those large particles eventually just settle out. But then, we have colloids, like milk. Milk is an absolute master of deception. It looks perfectly uniform to our naked eye, but if you put it under a microscope, it's actually a heterogeneous mixture, where tiny fat particles remain completely suspended without ever settling. Crazy, right? Moving right along to Section 2, particle size and light, the microscopic behavior of mixtures. To really understand milk's little optical illusion, we have to look at the microscopic maths. Solutions have particles smaller than 1 nanometer. That is so unimaginably tiny, they are practically invisible. Suspensions, on the other hand, have massive particles, well, relatively speaking, measuring greater than 1,000 nanometers. And colloids? They sit right in the middle, ranging from 1 to 1,000 nanometers. It's these exact microscopic boundaries that completely dictate the physical behavior of literally everything we interact with. Just watch what happens when we shine a laser through these 3 different mixtures. Up at the top, in the salt water, that red beam is completely invisible as it passes through. But down in the chalk powder water and the milk, the path of the light suddenly illuminates. This scattering of light by suspended particles is a truly brilliant phenomenon, known as the Tyndall Effect. So, let's put your analytical skills to the test here. Why exactly do we see the laser beam in the milk, but totally miss it in the salt water? Think back to those particle sizes we just talked about. Salt water is a true solution, right? Its particles are smaller than 1 nanometer, way too small to scatter any light. But milk is a colloid. Its particles are quite literally the perfect size to bounce that laser light right into our eyes, revealing the beam. All right, Section 3, the science of separation, exploiting physical properties. First up in our lab is crystallization. By definition, this is a method for separating a pure solid from a saturated solution. But what is the actual physical property we're exploiting here? Well, it's temperature-dependent solubility. Simply put, most solids dissolve way better in hot liquids than they do in cold ones. And here is what that process actually looks like in action. First, we heat up a solvent and dissolve our solid into it until the solution is completely 100% saturated. We filter it. And then comes the crucial step. We allow that hot solution to cool down very slowly. Because the solid is much less soluble at those lower temperatures, it naturally separates out. And that slow cooling, it gives the particles enough time to stack perfectly together, forming beautifully shiny geometric crystals. Okay, let's dive into another absolute essential technique, distillation. We use this when we're dealing with miscible liquids, liquids that mix completely together, like water and acetone. You obviously can't just filter those out. Instead, distillation exploits the distinct differences in their boiling points. This allows us to vaporize and then condense very specific liquids. In a standard laboratory setup, we heat the mixture right there in a distillation flask. Because acetone boils at just 56 degrees Celsius, but water boils at 100, the acetone vaporizes first. Those vapors travel down into the condenser. That's the angled tube you see wrapped in a cooling water jacket.
The cold temperature instantly condenses that vapor back into a pure liquid, which then drips down into the receiving flask, perfectly separated.
Let's completely shift gears to a different type of separation: paper chromatography. This technique separates dissolved compounds, like the different dyes that make up black ink, based on their differential movement rates through a medium. And in this case, that medium is simply paper.
When we dip just the bottom edge of the paper into water, capillary action draws the moisture upward, and it carries the ink spot right along with it. Because the different color pigments interact differently with both the water and the paper fibers, they actually travel at completely different speeds. It is essentially a microscopic race that separates a single boring black dot into a brilliant rainbow of distinct colors. Now, let's rapidly run through a few more crucial techniques you absolutely need to know. Separating funnels exploit density to basically drain heavier liquids like water right out from under lighter liquids like oil. Sublimation exploits the super unique solid-to-vapor transition of substances, like camphor, to separate them from standard solids. Coagulation uses chemicals like alum to clump fine, muddy particles together so they settle. And finally, centrifugation uses rapid spinning to push heavier particles outward based on their density, which, fun fact, is exactly the technology hospitals use to separate the components of your blood. Moving on to Section 4, Indian Knowledge Systems Heritage. Ancient wisdom meets modern science.
You know, ancient wisdom often perfectly mirrors modern science. For generations over in Kannauj, Uttar Pradesh, traditional perfume makers have been using the Deg-Bhapka distillation method to extract these beautiful earthy fragrances into natural mitti ka itar. And think about traditional spinning games, right? Like Fugati in Marathi or Kikli in Punjabi. When you lock arms and spin super fast, you feel that intense outward pull. Well, that is the exact same centrifugal force we just saw used in modern medical laboratories.
We can also see this incredibly rich scientific heritage all along India's vast coastlines. Local communities have long mastered the art of crystallization. They produce Panga salt by boiling concentrated sea brines and Kannauj salt by patiently allowing seawater to evaporate under the sun. It is a really wonderful reminder of just how deeply embedded this science is in our culture.
Finally, Section 5, Master Chemistry at Nudge. Test your higher-order thinking skills. So now it's absolutely time to put your analytical skills to the ultimate test over on edunudge.in. The platform is seriously packed with CBSE-aligned question banks and competency-based scenarios that are perfectly designed to stretch your brain. And hey, if you ever find solubility graphs or mass by volume calculations a bit tricky, their unique 5-step nudge system breaks the maths down beautifully. You'll be solving complex problems with total confidence in no time. Understanding the microscopic behavior of mixtures really is the key to separating them. It's a skill that's vital for everything from purifying the water we drink to creating life-saving medicines. So please don't let your learning stop here. Subscribe to the edunudge.in platform to practice absolutely all question types, from MCQs and assertion and reasoning to short answer, long answer, and even image-based problems. Put your newly acquired skills to the test. After all, if ancient perfume makers could master the highly complex physics of distillation centuries ago, what modern scientific breakthroughs are you capable of discovering next? Keep exploring, and I'll see you in the next explainer.